Alright, here are the properties of ideal gases. So ideal gases have negligible volume, right? Because they kind of just expand into whatever space they're in. So they don't really take up any volume, ideally. And ideal gases have no IMFs, or rather little to no IMFs. So what that means is that they don't repel or attract one another. And they're also randomly moving about, as mentioned earlier. And when they collide, there is no energy loss between them. Now, these aren't always true since we're in the real world. This is only in the perfect world, but because we're in the real world, these aren't always true. But they do help with the calculations and makes everything more accurate and easier for us to do. Now, next one is how do you keep a gas ideal? It's pretty simple. You keep the temperature high and the pressure low. Now, ideal gases are most ideal at lower pressure. So the lower the pressure, the more ideal a gas is. Keep that in mind. Now with that being said, let's Alright, now with that being said, let's talk about the ideal gas law equation, which is PV equals nRT. Oh geez. Was nRT. Now, this can be used to calculate many things, such as the temperature, pressure, volume, moles, and even R. Now, P is pressure in atmosphere. Make sure it's in atmosphere. Now, volume is in liters. Has to be in liters. Now, N is the number of moles of gas that you have or you're looking for. Right. Now, R is a constant, which equals 0.08206 liters atmosphere over moles Kelvin. And T is the temperature in Kelvin. And how do you get Kelvin? You do 273 plus C equals Kelvin. Plus your degree in Celsius, yeah. And so yeah, that's your equation whenever you're trying to figure something out with ideal gases. So let's do a practice problem. If you have 4 liters of gas in, let's say, 2 atmosphere and at 0 degrees Celsius, all right, how many moles of gas do you have? So you're solving for N, right? So you do PV divided by RT equals N. So that's 4 liters times 2 atmosphere divided by 0.08206 and 273 Kelvin. So liters atmosphere moles Kelvin. Now the liters cancel out, the pressure cancels out, and the Kelvin cancels out, and you're left with moles. So that works out pretty well. So now you do 4 times 2 divided by 0.0206 times 273, and you have 0.357 moles of gas. Oh geez. Moles of gas. So yeah, it's pretty simple. Now let's talk about the density, because this will come up on your exams or tests or quizzes. Now, there is a really simple equation to figure out the density, and that equation is molar mass equals density times R times T. over P. So dirt over P. Now, this equation is derived from the ideal gas law equation, but we're not going to go over that yet because it just takes too much time for this video. So yeah, so if you're trying to figure out the density of, let's say, oxygen, right, at, let's say, 0 degrees Celsius and at 2 atmosphere, right, oxygen, which is 32 grams per mole, is the molar mass, and 0 degrees Celsius is 273 Kelvin. Once again, you have to have all the same units. In atmosphere, which is good. Now you're solving for density, so to multiply by P. So molar mass times P times pressure divided by RT equals density. Now molar mass, which is 32 grams per mole, times the pressure, which is 2 atmosphere. Alright, divided by RT, 0.08206 liters atmosphere moles Kelvin. That's the units for R, times the temperature, which is 273 Kelvin. Now your atmosphere cancels out, right? Your moles also cancel out, and the temperature cancels out. So now we do 32 times 2 divided by 0.08206 times 273, which equals 2.86. Now you have grams, or rather your units are grams in liters, so you have grams per liter. And those are the units for density, mass over volume. And that's how we do density problems. So remember this equation because it will be your friend. Now, next up is diffusion and speed of gases. So let's talk about that real quick.